Our first question is from a grade 11 November 2015 exam paper. So we have question 4 that reads as follows. In the diagram below, a 2 kg block is connected to a 1 kg block by means of a light inextensible string. So because we know that there is a string, we need to take into consideration tension force when calculating. The blocks are pulled up an inclined plane, which forms an angle of 28 degrees to the horizontal. The sides of the block which touch the inclined plane have the same surface area. The kinetic frictional force between the 1 kg block and the inclined plane is 4 newtons, while the kinetic frictional force between the 2 kg block and the inclined plane is 8 newtons. So our first question, question 4.1.1, draw a labeled free body diagram showing all the forces acting on the 1 kg block. So because we have a mark allocation of 5 marks, this indicates that we need to show 5 forces that are acting on the 1 kg block. The mark allocation indicates how many forces you need to display. So use that as a guideline. So we have question 4.1.1. This is our object, our 1 kg block. I'm going to include the incline so it makes it easier for me to draw my forces. So we have a gravitational force that acts straight down. You can display that as Fg, or you can display that as Fw, or just W. That is completely up to you. Whichever notation you prefer to use, you can stick with that. So that is our first force. We need 4 additional forces. Now, because we know our object is on a surface, that indicates normal force that is perpendicular to the surface on which the object is on. Now, normal force can be represented as Fn, a lowercase n, or a capital N. That is completely up to you. Now, in addition to that, we were told that the kinetic frictional force between the 1 kg block and the inclined surface is 4 newtons. So we know we have kinetic frictional force that is acting on this object. Because our object is moving up the incline and friction is a force that opposes the motion of an object, our frictional force will act in the opposite direction to the motion of our object, which means our frictional force is acting down the slope. Now that's 3 forces. We need 2 additional forces. So if you notice, we've got a string that connects the 2 kg block and the 1 kg block. And when we have a string, we have tension force. So which direction is the tension force acting in the 1 kg block? Is it acting up the incline or down the incline? Now there's a rule that we can follow when figuring out the direction of tensional force. So tension always acts along the string but away from the mass. So we are looking at the 1 kg block. This is along the string. Now let us figure out which is along the string but away from the mass. So away from the mass could either indicate up or down, because both directions up and down are moving away from the mass, but only one direction is away from the mass and along the string. So because the string is on the left hand side of our 1 kg block, our tensional force is going to act down the slope. So down the slope is along the string but away from the mass. So that is tensional force. Next, we can see that there is an applied force of 30 newtons that is pulling both blocks up the incline. So that is going to be an applied force acting up the incline. So if you notice, we've got applied force, normal force, kinetic frictional force, tension, and gravitational force. That is 5 forces for our 5 marks. Now, I'm going to also include my components of Fg. You do not need to include that for the marks. The reason that I'm going to include it is because it makes it easier when I'm calculating. Because sometimes when you're in a rush, you're trying to calculate as fast as possible before you run out of time in an exam, you might forget those forces. So it's important, or not important, but it is preferable to include it so that you don't forget it. You can just look at your diagram and you can see, okay, there is the parallel and perpendicular component of Fg. So we know our perpendicular component of Fg is going to act along the same line as our normal force. Now you can represent this as Fgy, or you can represent it as Fg perpendicular, whichever is up to you. I just prefer to use Fgy. Now Fgx will be in this direction to complete our triangle, but I don't like to squeeze everything there in that corner. What I like to do is I like to move Fg parallel or Fgx, whichever you prefer to call it, up so that it exits my object. I've not changed the force, it's still exactly in the same position. I've just moved it up. So this is now going to be my Fgx. So as you can see, kinetic frictional force, Fgx, and tension are acting down the slope, whereas applied force is acting up the slope. Now let us try to draw the free body diagram of our 2 kg object. It's not required for this particular question, but it makes it easier for us to have a free body diagram so we can see all the forces and their directions of the 2 kg object for when we are calculating. So this is going to be our 1 kg block. And this will be our 2 kg block. So once again, I'm going to include the slope to make it easier. Now our 2 kg block, because this object has mass, it is going to have gravitational force acting straight down. And because this object is on a surface, it is going to have normal force acting perpendicular to the surface on which the object is on. So that's 2 forces that we've accounted for so far. Our question then states, while the kinetic frictional force between the 2 kg block and the inclined plane is 8 newtons. So we know by that statement we have a kinetic frictional force that is going to act in the opposite direction to motion. Our motion is up the incline, therefore kinetic frictional force is going to act down the incline. In addition to the 3 forces that we've accounted for, we also have tensional force. Now, let us try and figure out in which direction is tensional force acting on the 2 kg block. Now, our rule that I've previously mentioned is tensional force acts along the string but away from the mass. So, away from the mass could indicate down the slope or it could indicate up the slope. But if you notice, the only arrow that is on the string is the one going up the incline. If you look at this arrow at the back going down the incline, there's no string there. So that means that our tensional force is going to act up the incline because that is the direction that is along the string but away from the mass. We do not have applied force that is acting on the 2 kg block. The applied force is acting on the 1 kg block that is pulling both the blocks up the incline. The only reason that both the blocks are moving up the incline is because the blocks are attached by a string. But applied force is not acting on the 2 kg block, it is only acting on the 1 kg block. So our free body diagram for our 2 kg object has now been completed. In addition to that, I'm going to include my components of Fg. So we have our perpendicular component, Fgy, that acts along the same line as normal force. And once again, I'm going to include my component Fgx coming out of my object instead of including it down here to complete my triangle. If you notice, this component here is parallel to this. I've not changed anything, I've just slightly moved it up. So we now have our free body diagram of our 1 kg object and our 2 kg object. Let us continue to the next question. So our next question is 4.1.2. State Newton's second law of motion in words. Newton's second law of motion states that when a net force is applied to an object of mass, the object will accelerate in the direction of the net force, and this acceleration is directly proportional to the net force and inversely proportional to the mass. What this means is that as the acceleration increases, the net force will increase, or as the acceleration decreases, the net force will decrease, and vice versa. Because acceleration is directly proportional to net force. In addition to that, mass is inversely proportional to acceleration, or you can say acceleration is inversely proportional to mass, which means that as one increases, the other would decrease. So if acceleration increases, that would suggest a decrease in mass. Or if mass were to increase, acceleration would decrease. So as long as one is increasing, the other would decrease. And if one decreases, the other would increase. Our next question, question 4.1.3, calculate the magnitude of the tension in the string connecting the blocks. So they've indicated magnitude, which means we are not going to include a direction, nor will we include a positive or negative sign. We are only going to include the value, which is the magnitude, and the SI unit of measurement of that specific quantity, which is tension. So let us start by writing down the known values, and then we can start to substitute that into our formula of F net equals MA. So let us now try to find out what values we know. In the diagram below, a 2 kg block is connected to a 1 kg block. So first of all, we have masses. So let us make a note of that. By means of a light inextensible string, The blocks are pulled up an inclined plane, which forms an angle of 28 degrees to the horizontal. The sides of the block which touch the inclined plane have the same surface area. The kinetic frictional force between the 1 kg block and the inclined plane is 4 newtons. So we have the kinetic frictional force of the 1 kg block, and that is 4 newtons. While the kinetic frictional force between the 2 kg block and the inclined plane is 8 newtons. So we now have the kinetic frictional force of the 2 kg block, which is 8 newtons. Calculate the magnitude of the tension in the string connecting the blocks. Let's see, what other information do we have? Okay, so we have the applied force from the diagram. There is an applied force of 30 newtons that is acting on the 1 kg block. So these are all the values that we have. So I'm going to take up the incline as positive and down the incline as negative. So that means whatever forces are going up the incline, I'm going to assume them to be positive, and whatever forces are going down the incline, I'm going to assume that to be negative. So let us start by writing out our formula, which is F net equals MA. From this point, we can now break up this formula into its different components. So F net can be broken up into all of the different horizontal forces that are acting on this object. So let us have a look at what horizontal forces are acting on our 1 kg block. So we can get this from our free body diagram. So we can see that we've got applied force moving up the incline, so that is going to be positive. We then have kinetic frictional force, our parallel component of Fg, and tensional force that are all moving down the incline, which means those three forces are going to be negative. So let us put that in. Now, from here, we have the value of applied force, we have the value of kinetic frictional force, and we need to try and break up the parallel component of our force Fg, which is Fgx, into its formula because we do not have the value of Fgx. And tension is what we are trying to calculate, so we are going to leave that as T. So let's try and get our value of Fgx, or rather our formula of Fgx. So let's go back to our diagram. Now in our diagram, we know that Fgx is going to be the force that connects over here. So let us redraw that triangle so we can try and figure out our formula for Fgx. So this is our object. We've got Fg going straight down. We have Fgy, and then we have Fgx. And that is our triangle. Now, we know the angle over here is going to be 28 degrees. This angle is always the same as the angle of our incline. Now, if you notice, Fgy is in an adjacent position to angle theta, which is 28 degrees. And our FGX is in the opposite position to angle theta. So that is important because it tells us or it indicates what sine or cos we are going to use. So if it's in the opposite position, we are going to use sine. If it's in an adjacent position, we are going to use cos. So the formula comes from our trig ratio. So because it's in an opposite position, I'm going to use sine. So sine of 28 degrees is equal to opposite, which is FGX, over my hypotenuse, which is FG. Now we can simplify that to solve for FGX by cross multiplying, and we'll end up with FGX is equal to FG sine 28. Now we know that Fg is our gravitational force is equal to the mass times the gravitational acceleration of our object. So we can further break up this formula into mg sine 28. And that is what we are going to use in our formula. So let us substitute that in. So we've now broken up our formula as far as possible. What we are now going to do is substitute all the known values into our formula and see what we are left with. So we have mass of 1 kg, kinetic frictional force of 4 newtons, and applied force of 40, or rather 30, not 40, 30 newtons. So this is going to be 30 minus 4 minus a mass of 1, gravitational acceleration of 9.8, sine 28 minus tension, which is what we are calculating, time, which is then equal to our mass times acceleration. Now, as you can see, we have two unknowns, which is tension and acceleration. Now, what that indicates is we are most likely going to use simultaneous equations whereby our two unknowns are t and a. So we need to then go and find a second equation, which will be obtained from our 2 kg mass. We will then equate those two equations to find tension. So before we jump ahead, let us finish up what we are currently doing. So all we can do is put this entire thing onto our calculator. So give me a moment to do that. So this is going to be our first equation. So even though we are calculating for t, I'm not going to make t the subject of my formula. I prefer to use the method of whatever I'm calculating, I make the other variable the subject of my formula. The reason being is that if I were to make t the subject of my formula in both equations, when I equate my equations, t is going to fall away and I will only be left with acceleration, which I would then have to calculate acceleration, then substitute acceleration back into one of the tension formulas to obtain tension. Now that seems kind of long. So what I'm going to do instead is I'm going to make A my subject in both formulas. If I were to make A my subject in both formulas, when I equate my equations at the point of A, T will still be within my equation. So the rule is whatever you are calculating for, make the other variable your subject. So let us now get an equation for our 2 kg mass. So we have our formula F net equals MA. We now need to break up F net into all the different forces that are acting on our object. So let's go back to our free body diagram and have a look at what forces are acting on our object. So as mentioned before, I'm taking up the incline as positive and down the incline as negative, which means T, or rather tensional force, is going to be positive, whereas kinetic frictional force and FGX are going to be negative. So this is then going to be tension minus kinetic frictional force minus FGX is equal to MA. Now we are going to break up FGX into the same formula that we did previously. So we're going to break up FGX into mass times gravitational acceleration times sine of 28. The only difference is in this specific case with the block 2, which has a mass of 2 kgs, instead of substituting mass as 1 kg as we previously did, we are going to substitute mass as 2 kgs. So let us start with that. So we have tension that remains unknown. We have kinetic frictional force, about 2 kg block, that was given as 8 newtons, minus mass times gravitational acceleration times sine of 28. We can then substitute our mass of 2 kgs times acceleration, which is unknown. From this, I'm going to substitute my values of mass, which is 2 kgs, and my value of gravitational acceleration, which is 9.8, sine 28 equals 2a. From here, I can put in this whole part into my calculator. Negative 8 minus 2 times 9.8 times sine of 28. And that gives me t minus 17,20 is equal to 2a. So I'm going to solve for a because I want a to be the subject of my formula. So I'm going to divide both sides by 2 in order to get rid of the coefficient of a. So this is then going to be t minus 17,2 all over 2 equals a. And that is equation 2. So as you can see, I have equation 1 on the left and equation 2 on the right. I now want to equate both equations. So let me move this to the top. That way I have space. So I want to connect my equations. I have equation 1, which is equal to equation 2 because both are a equals something. So on the left, I have 21,4 minus t equals t minus 17,2 all over 2. So as you can see, because I've connected my equations at the point of A, t is within my equation. If I had solved for t and connected my equations at the points t, I would then have a in my equation instead of t, which is what I want to solve for. So let us now solve for t. So what we can do here is we can cross multiply. So we'll multiply the 2 on the left side. That is going to give me 42,8 minus 2t is equal to t minus 17,2. I'm then going to move everything that has t in it to the left side and everything that is a constant to the right. I can then add up. So that's going to be negative 3t is equal to negative 60. From here, I can divide by negative 3 on both sides, and that is then going to give me a value of T, which is my tension, as 20 newtons. Keep in mind that tension is a force, therefore it's measured in newtons. So all we did was break up both objects into their formulas using the horizontal forces. Once we were able to do that, we ended up with two unknowns, tension and acceleration. From that point, we equated the two formulas and solved for tension. Let's have a look at our next question. So we have question 4.1.4. How will the acceleration of the system change? Write down only increase, decrease, or remain the same. Okay, so it states that the two blocks are interchanged so that the 30 Newton force is now acting on block 2, which is the 2 kg block, along the inclined plane as shown in the diagram below. So you can see the difference between the two diagrams now. So previously we had the 30 Newton applied force acting on the 1 kg block, and the 1 kg block was higher up the incline as opposed to the 2 kg block. Now the blocks were interchanged, meaning that they were swapped. So where we had the 1 kg block, we've put the 2 kg block. And where we had the 2 kg block, we've put the 1 kg block. Now the applied force of 30 newtons is acting on the 2 kg block, and the 2 kg block is higher up the incline as opposed to the 1 kg block. So our question 4.1.4, how will the acceleration of the system change? Write down only increase, decrease, or remain the same. So the acceleration of our system would remain the same. It would not change. Something interesting to take note of is that our acceleration of our inclined slope is dependent on the angle of inclination of that slope. The reason being is because our force Fgx, which is the parallel component of gravitational force, is dependent on the angle of inclination of our slope. So if our angle were to increase, our force Fgx would also increase. If our angle of our slope were to decrease, the force Fgx would also decrease. And that increase or decrease would affect our acceleration. However, in this particular case, because our slope has not increased nor has it decreased, our acceleration remains the same because our forces Fgx remain the same. Now we have question 4.1.5. How will the tension in the string connecting the two blocks change? Write down only increase, decrease, or remain the same. So the tension connecting the two blocks would decrease. The reason being is because the lighter object is connected to the end of our slope. So in a sense, you can think of it as if you were to pull up a lighter object as opposed to pulling up a heavier object. So when you pull up a lighter object, there's less tension in the rope as compared to when you are pulling up a heavier object. When you pull up a lighter object, you use less force because the object is lighter, it has a smaller mass. Pull up a heavier object, it has more mass, therefore there's more force required to pull that object up, which means that the tension in the string would be greater if the object is heavier and less if the object is lighter. So the reason that our tension decreases is because we now have a lighter object or a object of smaller mass that is being pulled by the string. Our next question is 4.2. In the diagram below, a 1 kg mass and a 2 kg mass are connected by an inextensible string of negligible mass, which means that because there is a string, we are going to have tensional force in both objects. The string is passed over a light frictionless pulley so that the masses hang down as shown. Initially, the system is held at rest. Question 4.2.1. Draw a free body diagram showing all the forces acting on the 2 kg mass. So something important to take note of is that because the mark allocation is 2 marks, we only need to include 2 forces. So if you look at the 2 kg mass, it is not on a surface, therefore it will not have normal force. It has mass. Any object that has mass will be subject to gravitational force. So because this 2 kg object has a mass, it will have gravitational force, which will be our first force. Because there's a string connected to this object, there will be tensional force, and those are our 2 forces for 2 marks. So let's start with our free body diagram. So we have our 2 kg block, which has tensional force going up and gravitational force going down. Keep in mind the rule: tensional force acts in the direction away from the object along the string. So away from the object will be either up or down, but the string is going up. So that means our tensional force will act in the up direction, which is away from the mass but along the string. Now I'm also going to include a free body diagram for my 1 kg mass. The reason I'm doing this is if we are going to do any calculations based on these objects, which we are going to do in question 4.2.2, at least we have the free body diagrams that will assist us in our calculations. So the 1 kg mass is the exact same situation. It has gravitational force acting down, and it has tensional force acting up. So our next question is question 4.2.2. Calculate the time it will take the 1 kg mass to move a distance of 1 meter when the system is released. When the system is released, because the 2 kg mass has a greater mass, it will then have a greater gravitational force as compared to the 1 kg mass. Because it has a greater gravitational force, that means it's going to have a greater force pulling it down as compared to the 1 kg mass, which means the 2 kg mass is going to move downwards, whereas the 1 kg mass will move upwards, because keep in mind they are connected by a string, which means that if one was to move down, the other would have to move up as the string would not stretch. It's going to pull the other object. So let us just indicate this on our free body diagram. So our 2 kg mass is going to move down, whereas our 1 kg mass is going to move upwards. Okay, once the system has been released though, so keep in mind, the system was initially at rest, meaning it was initially stationary, and then the system was released. So all of a sudden, the 2 kg mass started to fall, and the 1 kg mass started to move upwards. Now, the 1 kg mass was displaced for 1 meter, meaning that it moved up 1 meter, which means that the 2 kg mass moved down 1 meter. So our question 4.2.2, calculate the time it will take the 1 kg mass to move a distance of 1 meter while the system is released. So we now need to calculate the time that it is going to take this mass or this block of 1 kg to move a distance of 1 meter. So we are calculating time. So let us write down what we already know. So we know that the displacement is 1 meter. I'm using delta y because it's vertical displacement instead of horizontal displacement, where I would use delta x if it was. In addition to that, we know that the mass of the object is 1 kg. What else do we know? We know that we are looking for time. We know that the initial velocity of this object is 0 meters per second. As it stated, the object was initially at rest. So let us now try to find time. So given the variables that we have and the fact that we are calculating time, we can make use of one of our four equations of motion. The equations of motion can be found at the back of your exam paper. So let's list our four equations of motion and try to identify which equation we are going to use. So we have our first equation of motion, which is Vf equals Vi plus A delta t. Vf squared equals Vi squared plus 2A delta y. We have delta y equals Vi delta t plus 1 over 2 A delta t squared. And lastly, we have delta y equals a half into Vi plus Vf times delta t. So something important is we are calculating time. Therefore, we need an equation that has time in the equation. We can't calculate for time using an equation that does not have time in it. So let us go through our equations and eliminate the equations that do not have time in it. So if you look at our first equation, it has time in it, so that can stay. If we look at our second equation, it does not have time, therefore it gets eliminated. We cannot use that equation. If you look at the third and fourth equations, they have time in it, so they can stay. Next, let us look at factors that we do not have. So we do not have the final velocity of this object. So we need to eliminate any equations that have final velocity in them. So our first equation has final velocity. We can get rid of that. Our last equation also has final velocity. Therefore, we can get rid of that. So we've now narrowed it down to one equation. So this is the equation that we are going to use. Now, let us try to substitute into this equation. So we have displacement as 1 meter. We have initial velocity as 0. We have delta t as our unknown, that is what we are looking for, plus 1 over 2. Now we do not have acceleration. We need to now try and get acceleration. We do not have that. So let us now try to figure out how we are going to find acceleration. So something important to take note of is that we have mass and we know gravitational acceleration because it is a constant. So it is possible for us to find acceleration using simultaneous equations of both our objects, which is something we previously did in question 4.1.3. So we're going to use the exact same method to try and find acceleration of this system. So let us do that. So before we even do that, we need to first identify our positive and negative directions. So because we have two objects moving in different directions, I'm going to take the direction of motion as positive, meaning that for my 2 kg mass, downwards would be positive, and for my 1 kg mass, upwards would be positive. So because I'm taking the direction of motion as positive, as compared to taking a single direction as positive, my directions for each object would be different in terms of being positive or negative. Now, this same rule or this same direction can be applied to objects or to questions that look similar to this. I'm sure you've seen this previously, whereby you have a table and there's two objects that are connected via a string that runs through a frictionless pulley, and in most of the cases the object is moving to the right and down. Now, in such a case, you can also take the direction of motion as positive, meaning to the right as positive and down as positive. So, if your objects are moving in two different directions, I would recommend that you take the direction of motion as positive. So, that means that down is going to be positive for my 2 kg block, and up is going to be positive for my 1 kg block. Now let us try to break up our blocks into their respective forces and try to find the value of acceleration. So I'm going to start with my 1 kg block. Now we have our formula: F net equals ma. We can break up F net into tension and gravitational force, keeping in mind that tension is moving upwards, which is the direction of motion. Therefore, tension will be positive. Next, we need to deal with gravitational force. Now, because gravitational force is moving downwards, whereas my direction of motion is upwards, that means gravitational force is going to be negative, and that is equal to ma. I can further break up my Fg force into the mass times the gravitational acceleration, and that is equal to ma. From this point, I can start to substitute. So that's going to be 1 times 9,8 equals 1a. That can then be simplified into t minus 9,8 equals a. Now keep in mind, I am trying to solve for acceleration, which means that I need to use the other variable as my subject. That is the rule that we previously used. So I'm finding acceleration, so I'm going to make tension my subject. So when I equate my equations, tension will fall away and I will only be left with acceleration. So that is equation 1. Now let's have a look at equation 2, which is going to be built or formed from our 2 kg mass. So we have our 2 kg mass, and we've got our formula F net equals ma. Now let us break up F net into its forces. We've got two forces acting on our 2 kg mass. That is tensional force and gravitational force. Now keep in mind we're taking the direction of motion as positive. Therefore, downwards is going to be positive because the 2 kg mass moves downwards, which then means that everything moving upwards for the 2 kg mass is going to be negative. So I'm going to have Fg minus tension in this case, which is then equal to mass times acceleration. I can break up Fg into mass times gravitational acceleration, and then I can start to substitute. So my mass is 2 kgs times 9,8 minus t equals 2a. From this point, I can put that into my calculator and get 19,6 minus tension equals 2a. Now keep in mind, I want to solve for tension. I want tension to be the subject of my formula. So for this particular equation, I'm solving for tension because I want to have acceleration in my simultaneous formula. So I'm going to move that 2a to the left, and I'm going to move tension to the right. So I've now made tension the subject of my formulas for equation 1 and equation 2. So you'll see when I equate my formulas, tension will fall away and I will only be left with acceleration. Now, from this point, I'm going to move all of my variables with their coefficients to the left, and I'm going to move all of my constants to the right. So this becomes 3a equals 9 comma 8. From this point I can divide both sides by 3, and that is then going to give me my acceleration of my system as 3,27 meters per second squared. Now that is the acceleration of my system. So you can see there was quite a bit of a process involved. That is why we had a mark allocation of 7 marks. If it was only just substituting into our equation of motion, at most I believe it would have been maybe 3 to 4 marks. But because we needed to use our simultaneous equations to get acceleration, there were some additional marks involved. So all we now need to do is substitute this acceleration into our equation of motion formula and then proceed to solve for delta t. So we're going to substitute 3,27, and that is going to give us 1 equals a half into 3,27 delta t squared. From here we can multiply a half times 3.27, and that is then going to give us 1,635 delta t squared. From this point we can divide both sides by 1.635, and that is then going to give us 0,6116207,951 equals delta t squared. Now, in order to get rid of the squared on delta t, because keep in mind we are only looking for time, we can square root both sides. And that is therefore going to give us a time of 0,78 seconds. So it took the 1 kg mass or 1 kg block a total of 0.78 seconds to move a distance of 1 meter. So all we needed to do was try to find time. Now we used our equation of motion to find time by substituting our displacement and initial velocity that was given. After we did that, we ran into an issue whereby we did not have acceleration. So we needed to then go and find acceleration. The method we used to find acceleration was similar to the previous method we used in question 4.1.3, whereby we created simultaneous equations for our two masses. Now, the important thing to take note of in this particular question was because we had objects that were moving in two different directions, I took my direction of motion as my positive direction, which means everything that was moving in the opposite direction of motion was taken as negative. This also resulted in having two different directions as positive and negative for both my objects. So because my 2 kg mass was moving down, everything going down was positive and everything going up was negative. And because my 1 kg mass was moving upwards, everything moving up was positive and everything moving down was negative. Now, let us proceed to question 5, whereby we will make use of Newton's laws of universal gravitation to solve our questions. So we have our first question. Gravitational force exists between the Sun and Earth. Question 5.1. State Newton's law of universal gravitation in words. So, Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses. Keep in mind, product refers to multiplication. So the product of their masses and inversely proportional to the square of the distance between their centers. Our next question is question 5.2. The mass of the Sun is 330 times greater than that of the Earth. So that means that whatever the mass of the Earth is, the Sun is 330 times greater. Think of it as if your friend is 50 kgs and you are 2 times greater than the mass of your friend. All you would do is to get your mass, you'll multiply your friend's mass by 2 because you are 2 times greater than the mass of your friend. Now, in this particular case, the Sun is 330 times greater than the mass of the Earth, which means that in order for us to get the mass of the Sun, we need to multiply the mass of the Earth by 330,000. Now, if you do not know the mass of the Earth, please don't panic. That information is found at the back of your question paper. Before we read the rest of our question, let us stop to calculate the mass of the Sun using the mass of the Earth. Now keep in mind that value of 5.98 times 10 to the power 24 can be found at the back of your question paper under the constants table. So to avoid having a very long number, what I'm going to do is I'm going to keep this as is, and this is in kgs. So let us go back to our question. The mass of the Sun is 330,000 times greater than that of the Earth. We've already discussed that and we've already found the mass of the Sun. The distance between the centers of the Sun and the Earth is 1.38 times 10 to the power 9 meters. Now keep in mind, whenever we are finding r, which represents the distance between the centers of the objects, we need to take from the center of object 1 to the center of object 2. Usually that means we need to include the radii of those specific objects. However, in this particular case, we were given the distance between their centers, so we do not need to take into consideration the radius of the Sun and the radius of the Earth. However, if you are interested in knowing the radius of the Earth, it can also be found under the constants table in your formula sheet. So we have our value of r as 1.98 times 10 to the power 9 meters. Now our question is, calculate the gravitational force that the Sun exerts onto the Earth. That is the force F. So let us now go and calculate that. So we're going to use the equation F equals G, which is a constant, times the mass of the Sun times the mass of the Earth, as those are our two objects in question. over the distance squared. Now we know that our radius has a value of 1.38 times 10 to the power 9 meters. So we can substitute that in place of r. We can substitute this in place of the mass of the sun. And our value of g is a constant that can be found under your constants table at the back of your question paper. Don't forget to include the squared on top of your distance for the distance between the centers because r is squared. If you forget it or exclude it, your answer is going to be incorrect. Now to get our final answer, all we need to do is put this onto our calculator and we should have the force that the sun exerts onto the earth. And that gives us a value of 413,32 times 10 to the power 24 newtons. And that is the force that the sun exerts onto the earth. Our next question, question 5.3, how will the gravitational force that the earth exerts onto the sun compare to the answer in question 5.2? Now keep in mind question 5.2 was the force that the sun exerts onto the earth. This question wants to find out how will the force that the earth exerts onto the sun compare to the force that the sun exerts onto the earth? And we need to state either greater than, less than, or equal to, and give a reason for our answer. So if you think back to Newton's third law of motion, which states that object A will exert a force onto object B, and object B will exert a force of equal magnitude onto object A. So it's an equal opposite reaction force. So in this particular case, our answer is going to be equal to, and the reason for that is because of Newton's third law of motion. Because the force that the sun exerts onto the earth is equal to the force that the earth exerts onto the sun. Now let's have a look at our next question. Our next question is from a November grade 12 2019 exam. So we have question 2 that reads as follows. Block P of mass 2 kgs is connected to block Q of mass 3 kgs by a light inextensible string. Both blocks are on a plane inclined at an angle of 30 degrees to the horizontal. Block Q is pulled by a constant force of 40 newtons at an angle of 25 degrees to the incline. Block P moves on a rough section, so the use of the word rough indicates frictional force. section AB of the incline, while block Q moves on a frictionless section BC of the incline. So if you look, we've got section AB that is rough, therefore it has friction. And on that surface AB, we have a 2 kg block P that is connected to block Q via a string. Because we have a string, we therefore have tensional force. Now, if you remember, we mentioned that tensional force moves along the string away from the mass or away from the object. Therefore, our tensional force for block P is going to move in that direction, which is up the incline, while our tensional force in block Q is going to move down the incline. And we have section BC that is frictionless, therefore there is no friction acting between the block and surface BC. In addition to that, we have object Q that has an applied force of 40 newtons that is acting at 25 degrees to the incline. Now, because our applied force is inclined, that then means that we have components of that applied force, similar to how we have components of weight or gravitational force, whichever you want to call it. So we're going to have a horizontal component of applied force and a vertical component of applied force. Question continues to state an average constant frictional force of 2.5 newtons acts on block P as it moves from A to B up the incline. So our block P, which is our 2 kg mass, has a 2.5 Newton kinetic frictional force that is acting down the incline as it moves between points A to B. Next, we have question 2.1. State Newton's second law of motion, which states that when a net force is applied to an object of mass, the object will move in the direction of the net force. This acceleration is directly proportional to the net force of the object and inversely proportional to the mass of that object. Next, we have question 2.2. Draw a labeled free body diagram for block P. So let us actually draw a free body diagram for both block P and block Q. That'll make it easier for us when we are going to do our calculation questions. If you read the next question, which is an 8-mark question, you can see that there is some calculation that we have to do. So that is how drawing a free body diagram for both block P and block Q will benefit us. So let us start by drawing a free body diagram for block P. So this will represent our object. Let us include our incline. And our object is inclined at 30 degrees to the horizontal. Now we can start by including all the forces that are acting on this particular object. So our question 2.2 has a mark allocation of 4 marks. Now whenever we draw a free body diagram, the mark allocation needs to correspond to the number of forces that we are going to include in our diagram. So because we have 4 marks, we need to then include 4 forces. So we have a gravitational force that is acting straight down because this object has mass. We then have a normal force that is acting perpendicular to the surface on which our object is moving. We then have tensional force that is moving or acting up the incline. In addition to that, we have kinetic friction that acts in the opposite direction of motion, which is down the incline. Now, in addition to that, I'm going to include my components of my gravitational force. So we know we have our perpendicular component that acts in the same direction as normal force, keeping in mind that the angle between FG and our perpendicular component is the same angle of our incline. So that is 30 degrees. Next, instead of drawing my parallel component FGX down there, I'm going to draw it coming out of my object, which is still the same thing. I'm just moving it up. Now, that is my free body diagram for block P. Let us now draw a free body diagram for block Q. So we have this to represent our object. We can include our incline to make it easier to draw our forces. And this is inclined at 30 degrees. Now, our mass Q has gravitational force acting on it because it has mass. It also has normal force acting on it because it is moving on a surface. It has tensional force going down the incline. Now keep in mind, we were told that surface BC is frictionless. Therefore, block Q will not have a kinetic frictional force acting down the incline. But we will have a applied force that is inclined at 25 degrees. So let us include that. So we can just draw a dotted line to show our horizontal, and then we incline our applied force at 25 degrees. Now, those are all the forces that are acting on our object. Now what we can do is break up these forces into their components, because keep in mind Fg has a horizontal and vertical component, and our applied force, because it is inclined, has a horizontal and vertical component. So let's start with Fg since we're already familiar with that. We have Fgy going straight down. I'm going to draw Fgx down the incline, and then we have our horizontal component of our applied force. I'm going to call it FAX, and we have a vertical component of our applied force, FAY. Let me make my applied force slightly longer. Okay. Now keep in mind that this is at an angle of 90 degrees. So we now have free body diagrams of both our objects. So that is now going to make the next question slightly easier for us to do. Now let's go back to our question and see what we have. So we have question 2.3. Calculate the magnitude of the acceleration of block P while block P is moving on section AB. Now keep in mind we have the value, or rather the magnitude of applied force. We have the magnitude of our kinetic frictional force. What we do not have is the tensional force and the acceleration. So just as we did previously, whereby we used simultaneous equations to find tension, we are now going to use simultaneous equations to find acceleration. Let us now attempt question 2.3, whereby we need to calculate the acceleration of block P. So like I mentioned previously, because acceleration and tension are unknown, we now need to create or build two separate equations and equate them to one another, or join the equations, if you want to refer to it as that. So let's start with block P. Let us now break it up into all of its values. So our equation is going to be F net equals MA. I'm going to assume up the incline as positive, which means my tension is going to be positive, my kinetic frictional force will be negative, and my force Fgx will be negative. And that is equal to my mass times the acceleration. Now, tension is unknown. Kinetic friction was given to us as 2.5 newtons, and the mass of block P is 2 kgs. So this is 2.5 minus. Now, before we actually get to our mass, which is on the right hand side of our equation, we need to break up Fgx. So let's try and do that on the side. So if this is now our object, and we have Fg moving down, we have Fgy that is in the same plane as normal force. And to complete that triangle, we have Fgx. Now, my Fgx is the same as what is in my free body diagram. We can even write it up here if we want to. It means the exact same thing. If you notice, both vectors are parallel to one another, so there's no difference. And this is a 30-degree angle. Now we need to try and see, are we going to use sine or cos for Fgx? How we identify that is, if you take note, this is the adjacent side to our angle, and this is the opposite side to our angle. So because this is the opposite side, we are going to use sine of that angle, because sine deals with the opposite. So this is then going to become Fgx equals to force Fg, which is equal to mg sine of 30 degrees. So let's plug that in. Mass times gravitational acceleration times sine of 30 degrees, which is equal to our mass. We previously mentioned that that was 2 kgs. Now, let us continue to substitute and try to simplify our equation. So we have tension minus 2,5 minus a mass of 2 times 9,8 times sine of 30 is equal to 2a. From this point, we can put this into our calculator. So we'll put in negative 2.5 minus 2 times 9.8 times sine of 30. And that gives us negative 12.3. Now, something important to take note of, something I mentioned previously, which is if you are calculating for variable 1, make variable 2 the subject of your formula. So whatever you are calculating for, make the other variable the subject, so that the variable you are calculating for will be within your equation once you connect the two simultaneous equations. Okay. So because we are calculating for acceleration, I'm going to make tension the subject of my formula. And that is going to be equation 1. Now, let us have a look at equation 2, which is our block Q. Now, in block Q, we are going to make the same assumption, take up the incline as positive because both our objects are moving in the same direction up the incline. Now, we have applied force, or rather the horizontal component of applied force, which is FAX, that is moving up the incline. Now, keep in mind, we are going to take FAX instead of FA because FA is inclined. Therefore, it's broken up into a horizontal and a vertical component. So, because we are taking into consideration all of the horizontal forces, keep in mind we are assuming the surface of our incline as the horizontal and the direction of normal force in FGY as the vertical. Okay, if you think back to what we previously did, whereby I told you to incline your vision or to incline your head so that when you look at this, that is Y and that is X, as opposed to how you normally do X and Y. So the whole goal of this is to now view everything inclined. So you can tilt your head or whatever you want to do to be able to see that your X, which is your horizontal, that is now your surface of your incline. And your Y is perpendicular to your surface of your incline. Now our force FA looks like this. And our force FG looks like that. So as you can see, those forces are neither in the Y or X horizontal or vertical direction. So as you can see, those forces are neither in the horizontal or vertical direction. They are inclined to those horizontal and vertical directions. That is why we take the components of those forces into consideration. So if we break up FA, that is then going to be FAX. As you can see, it is now in the horizontal direction. So let us just show the incline, which is 25 degrees. So let us now try to investigate what are we going to use for FAX? Are we going to use cos or are we going to use sine? So before we do that, let us quickly complete our triangle. So as you can see, FAX is in the adjacent position to the 25-degree angle. And our FAY is in the opposite position, or instead of thinking about positions, you can think of sides. So FAX is the adjacent side of our triangle, whereas FAY is the opposite side of our triangle. Now, how do we figure out which side is opposite and which side is adjacent? So if something is opposite, or if the side is the opposite side, it is going to be the side opposite to theta. In this case, our 25-degree angle is that theta value, or instead of thinking of theta, you can just think of any angle. So if the side is opposite to the angle, you refer to it as the opposite side. If that side is below or next to the angle, it is then the adjacent side. Now keep in mind, next to the angle can refer to your hypotenuse or your adjacent. But you know that your hypotenuse is the inclined side, the longest side, the side opposite the 90-degree angle, which is our main force, FA. So this is our hypotenuse. So the only other side that is next to our angle theta is the 25 is the side FAX. So that will be the adjacent side. Now, because FAX is the adjacent side, we ask ourselves, okay, which identity uses adjacent? Is it cos or is it sine? Now, we know that cos makes use of our adjacent. So that is going to be cos of 25 equals to adjacent, which is FAX, over hypotenuse, which is FA. That then can be simplified into FAX equals FA cos 25. So that is what we will substitute in place of FAX. And that is the first force that I'm going to take note of in my formula. And that force is moving in the positive x direction, or the positive horizontal direction, or another way of thinking about it, it is moving up the incline. So I'm going to make that positive FAX. Now, that is the only force I have that is moving up the incline. The only forces that The forces that are now moving down the incline, which I took as negative. So because I took up the incline as positive, it then suggests that all the forces moving down the incline are negative. So that is then going to be minus tension minus FGX equals MA. Now let us break up FAX into what we previously found, which is FA cos 25 minus tension, which is unknown, minus, now if you think back to the previous formula that we broke up, we already identified that FGX is mg sine 30. You can even find the same thing if you were to break up this particular diagram that we have up here. It will give you the same end result. So that is going to be mg sine 30 equals MA. So let us put 40 cos of 25 into our calculator, and that gives us 36,25 minus t. Now we can put negative 3 times 9.8 times sine of 30 into our calculator, and that gives us negative 14,7, and that is equal to 3a. From here, we can put these two constants into our calculator. Don't forget about the sign that is associated to that constant. Don't leave out the negative sign in front of 14.3. So let us put this into our calculator. So we have 36.25 minus 14.7, and that gives us 21.55. From there, we can solve for t. So we are going to have 21,55 minus 3a equal to t. So our whole goal of this was to solve for t, because like I mentioned before, whatever you want to find, which in this particular case is acceleration, make the other variable your subject, so that when you connect both equations at the second variable, which in this particular case is point t, you are then going to have the variable that you want to find, which is a, within your simultaneous equation. So we are going to connect both equations at point t. So that is going to be equation 1 equal to equation 2. So we are connecting both equations at point t. Now keep in mind, if one of your equations was negative t equals to something, you cannot connect it. You have to have the same thing on both sides. If you're connecting negative t and negative t, or 2t and 2t, or t and t, it has to be the same thing to connect. So we'll substitute our first equation, which is the one on the left, to a plus 12.3 equals our equation on the right, equation 2, 21, comma 5 minus 3a. So we now need to solve for A. But let us quickly take a step back and recap what we are actually doing, because I know this was quite a long experience. There was quite a number of steps involved, and you might have forgotten what our original goal was. So we were asked to calculate the acceleration of block P. Now keep in mind, tension and acceleration are unknowns. So based on that, we now know we need to use simultaneous equations. Whenever you have two variables unknown in physics, that is a sort of indication that you need to try and approach it using simultaneous equations. Or if you have an alternative method that you prefer to use, you can also do that. But for this particular question, I decided to go with simultaneous equations. Now, from here, I broke up my forces of block P into their equation and I solved for T. That gave me my equation of T that had acceleration in it. That was my equation 1. Next, I broke up my forces, more specifically my horizontal forces of block Q, and that gave me an equation whereby I had T equals to something in terms of A. Now from there, because I had both equations whereby the subject was T, I was able to equate them and have A within my new equation. So I can now solve for A. So in order to solve for A, what I'm going to do is I'm going to move everything that has A to the left and all the constants to the right. From here, we can see that 2a plus 3a is going to give us 5a, and 21.55 minus 12.3 gives us 9.25. From here, we can divide both sides by 5, and that is therefore going to give us a value of A as 1.85 meters per second squared. Don't forget about the unit of measurement. So that is now the acceleration of block P. Let us move on to our last and final question. Our last and final question is question 2.4. If block P has now passed point B, how will the acceleration compare to that calculated in question 2.3? So basically, what is happening is our block P has now passed point B. So it's past this point, and we now have block P in the frictionless area. So this is now block P. It's now in the frictionless surface BC, or rather, it is now on the frictionless surface BC. So our question wants to know, how will the acceleration of block P on the frictionless surface BC compare to our acceleration calculated of block P during section AB, whereby there was friction acting on the block? So our answer is going to be greater than. The acceleration of block P where there is no friction will be greater than our acceleration of block P whereby there is friction. So let us do this to explain. So think about it like this. If this is our block P and we have tension that's pulling the block up the incline, we then have Fk pulling the block down the incline. In addition to that, we have FGX also pulling this block down the incline. But if we were to remove kinetic friction from this free body diagram, we would then have one less force pulling our object down the incline, which means our object will be able to accelerate at a greater acceleration up the incline. Think about it as though if you have two friends pulling you backwards while you are trying to run forward, if one of the friends lets go, you'll be able to run forward at an easier pace, or you'll be able to run forward much faster as compared to when there were two friends pulling you back. So, because kinetic friction has been removed, our object is now able to accelerate at a greater pace or a greater rate. So, our answer to this particular question is going to be greater than, and our answer is because our kinetic friction has been removed. Alternatively, you can also state because your net force is going to be greater, and net force is directly proportional to acceleration. Therefore, your acceleration will be greater if your net force is greater. The reason that I say net force will be greater is if you think about it like this: net force for this particular free body diagram will be tension minus Fgx, whereby if there was kinetic friction involved, net force would be tension minus Fgx minus Fk. So you are subtracting more things, so your answer will be less. It's kind of like if you go to the grocery store, or if you go to the shop and you buy more items, you'll have less money. Whereas if you buy less items, you'll have more money. So if you think about it like this, let's state for this particular example, let's say tension is 10 and FGX is 2. So this will also be 10, this will also be 2, and let's say kinetic friction is 1, just as an example. That'll give this a value of 8, whereas this will then become 7. So you can see that whereby you subtracted more items, you have a lesser value. So if kinetic friction is involved, you then have one additional force that is pulling this object, or a force that is pulling this object down the incline. If you remove kinetic friction, you then have less forces pulling your object down the incline, therefore the acceleration up the incline will be greater.